Hi, everybody. My name is Justin Castilla. I am a senior developer advocate at Redis, which is a little database company. Some wacky, interesting climate things have happened in the last, I'd say, 4 or 5 years, and I wanted to talk about it a little bit. So let me get started. What's that smell? It was the top of the question for the last 4 or 5 years in California. Spoiler alert, wildfires. And I had a lot of time at home, and I had a lot of time to just play with hardware, and I started this little project. So I'd love to talk to you about it. Let's get some introductory facts about the wildfires that were affecting the North American West Coast. In 2020 alone, 10.274 million acres of land were burned. That is among 58,258 individual fires. Actual financial loss, about $19.8 billion minimum. And unfortunately, that led to 1,200 to 300 excess deaths, and they attribute this to exposure to wildfire smoke. Also, we learned about fire tornadoes. I did not know that these existed. They can go up to 400 miles per hour, and California gets earthquakes and they get wildfires, but I did not know about tornadoes, and that was really kind of scary. And so what happens when wildfire smoke is of a large concentration around us? Well, it affects our eyes and our respiratory tract. It exacerbates bronchitis, asthma, actually leads to heart failure because your heart has to work against a lot of these particulates that are going into your system. And it does lead to premature death. Personally, when I was affected by the wildfire smoke, I had a sore throat. My voice was absolutely shot. Sounded like I was screaming in a metal concert the night before. And I got a huge headache, just because not just the smell, but just like constantly breathing in all that bad stuff really, really does affect you. And there's also the psychological factor. The beginning slide here, this is actually a picture of the red day. Now, the red day was September 9th, 2020. And that's when most of Northern California, primarily in the Bay Area, the sky was red. That's just no other way to describe it. It was very dark. Birds were freaking out. They were not chirping. Street lights were still on at like 10 a.m., 11 a.m. It was dark. It was very quiet and very eerie. And it was because of all the wildfire smoke got so high in the atmosphere that it started to block some of the spectrum of light. So we saw red and orange, we didn't see the blue light coming in. That was very psychologically affecting. So a little bit more background, because I'm telling you, it's worth it to like get all this starting knowledge. We measure wildfire smoke with particulate matter, specifically particulate matter 2.5 micrometers or smaller. Anything larger than that will be filtered out by your lungs and the cilia in your lungs. 2.5 and smaller, that's when it gets a little bit scarier. That's when it starts traveling into your lung sacs and sort of closer to the blood barrier between the oxygen in your blood. And it could actually go through and make its way into your bloodstream. So that's what we really, really want to look at as far as measuring like how healthy it is outdoors. And I almost have this memorized, as most people on the West Coast all the way up to Canada have, but this is basically what we live by. The values on the left are the AQI, and then it basically tells you how good it is outside, whether or not you should be wearing a mask or if you should be exercising outdoors, things like that. So one of the best ways to measure this is a device right here, this little particulate matter sensor. And this was born of inspiration from this website called purpleair.com. Now, Purpleair is a crowdsourced website where they sell you a sensor, you install it outdoors or indoors, and they use this particular sensor within that housing. And it reports back to their main website the AQI value. and then you can create a crowdsourced map. And that's really great because then you can see, a local map of your current area down to like, oh, somebody 3 blocks away has, this sensor, so I can sort of see what the AQI index is. And basically how it works, I'm not going to get too deep into it, but basically it uses lasers. It takes a little puff of air inside its machine, shoots lasers across that air, and the dust and the particulate matter will scatter the laser. And it's absolutely magic to me, but however they figured it out, lasers will go across the dust and it will be able to count the amount of particulate matter within the air based off of how much of the laser light is actually going through. And they can get it down to 2.51 microns in size. So I think it's really, really interesting. And most importantly, it spits out serial information. So I can read it just by parsing out some bytes. And it's relatively inexpensive. I can get these off of Amazon or eBay or DigiKey for about maybe $13 or $14 at a quantity discount. So this is very approachable to building on your own. So I connected my sensor to a Raspberry Pi Pico W. Now, a Raspberry Pi, as we all know, is like the awesome little tiny computer. You can pretty much run any Linux flavor on it with a desktop and everything like that. That's great. That's overkill for what we actually want. We don't need all of that overhead. So I chose the Raspberry Pi Pico W. So this is more of a microcontroller, which means it does run one script of code over and over and over. Fortunately, we can run MicroPython. MicroPython is a flavor of Python that is designed for microcontrollers. There's CircuitPython and MicroPython. And those are for the Raspberry Pi Pico, Pico W, and I think a couple Arduino units actually can have it ran on the microcontroller. But yeah, it has dual core processors. That has enough RAM and onboard memory to actually run simple applications and simple scripts like we'll see here. And as you'll see, MicroPython is not a whole lot different from regular Python. So that's actually really nice. And it's only $6 right now. The chip shortage has sort of alleviated, so we can get them at some decent prices, just as some quantity limitations. So, this is not a perfect to-scale diagram, but essentially all you have to do is connect 3 wires from the sensor to the Raspberry Pi Pico, and you could solder it, or you can put on a breadboard or anything like that. It's not too difficult. And I connected Redis to the Raspberry Pi Pico and the sensor. Now, Redis is, I won't give you too much of a sales pitch, it's a NoSQL database, so no rows and columns. It stores data structures, and it doesn't store them on a hard drive traditionally, it stores them on RAM. So it's extremely fast. It's not beholden to any kind of schema or required data fields. You can kind of throw into it what you want. And a lot of time, these data structures are just really efficient for the task. So a lot of people use Redis for caching. I'm using this for a lot of different data structures just to make sure everything runs really fast. Okay, so let's start looking at a little bit of code. You literally have to do the most basic things when you're running a microcontroller. So right here, you'll see that I'm actually connecting to my wireless AP. And I have all the files included in a repository that I'll share at the end of my my talk. But basically, there's no environment variables exactly with a microcontroller, because the environment is exactly what you write of it. So I included a secrets file that just includes my my Redis cloud password and host information and my Wi-Fi password and SSD and all that. So, all right. So we're connecting to the wireless right here, and I'll just let me know like what IP I'm connected to, and that's so I can actually track it, make sure all my sensors are connected. And then at the bottom, I'm connecting to my Redis client, and I'm very, very fortunate that somebody actually wrote a Redis library for MicroPython. as well as this sensor, Pomerone, which is a popular Raspberry Pi retailer. They have somebody who wrote a client, and it's absolutely amazing. So yeah, so here I am connecting to Redis via wireless, and everything within the Raspberry Pi controller has to be within a while true loop, so it just runs constantly. And with the sensor, I want it to run constantly, and I want it to actually check the air. So what I'm doing here, if countdown timer is less than or equal to sensor interval, I want to have my sensor announce to Redis that, hey, I'm still alive, I'm here, I'm kicking, I'm chooching, I'm making sure that everything, I'm checking the values. And that's actually really important, so I can actually report back to a front-end API of what sensors I have available. Also, for visualization with Grafana, I'll use it to actually show what sensors I can choose from if I want to look at their AQI history. Okay, so at the try clause, I'm actually going to be reading from the sensor. Raw reading just pulls the raw data from my actual plan tower unit that's connected to the PicoW. I do have to do a little conversion. So from AQI, from the raw reading, which is purely the number of particulates in the air, to AQI, you actually have to put it through a pretty complex set of mathematical algorithms based off of the tier. If it's from 0 to 50 particulates per square meter or cubic meter, then you apply these values through it. And if it goes from 51 to 100, different values. And that is also included in the repository. It's visually not very interesting, but it is good to know every once in a while if you want to go through it. The PicoW also has an onboard temperature reader. So that's like a free bonus sensor reading that I thought would just be interesting to have. I have these throughout my house. So sometimes I'm interested, what temperature is it in the greenhouse? What temperature is it in the spare bedroom, or in the bedroom, and the kitchen? You'll see at the bottom of this code snippet, results equals redis.xadd. Now that is adding the raw reading, the particulate matter, the AQI, and the temperature to a stream. Now, a stream data structure is basically, in Python terms, you could imagine it as a long list, an immutable list based off of time. And the list element is a dictionary, you could say. So a stream entry will include a timestamp of when it was included into the stream. And for me, I'm adding the target, which is the location. So office, bedroom, spare bedroom, greenhouse. And then the particulate density, the AQI value, and the temp. So 4 different things added to each stream entry. And each stream entry is going to have an ID, which is going to be a timestamp. And here at the end, I am actually counting down the timer based off the sensor interval. Now, the sensor interval, I'm taking sniffs of the air. I'm taking readings of the air every 5 seconds. That's so I can actually demonstrate how things change. Realistically, air quality average isn't going to change a whole lot every 5 seconds. So I think a more realistic air reading interval would be 10 minutes. So you wouldn't have to have your sensor report in every 5 minutes like I am doing, but you would want to have it report maybe every hour so you know if it's still alive. So here's a visualization. I'm a visual learner, so I want to share with you how I visualize this. The stream data structure for Redis, again, is basically a large list or collection of entries. They don't all have to be the same. There's no schema. But here I am storing the office with PM 2.54, AQI of 16, that's clean air, and the temperature is a comfortable 67.75. And again, the stream is immutable, so you could trim it, you can shorten it, but you can't change anything within it, and you cannot remove existing IDs within it. So if I could do it with one sensor, it makes sense that I can actually do this with multiple sensors. So I have been collecting over the last, I'd say 2 or 3 months, Raspberry Pi Pico sensors, and programming them all into different rooms and having them report to one stream. And I want to show this real quick here. You'll see the office and the kitchen are they're sharing the same timestamp. Remember I was saying those timestamps are IDs of the streams? They're sharing the same timestamp, which is very rare. But when it does happen, the sequence changes. So office has an ID ending in 0, and then the kitchen has an ID ending in 1. And that's how we can actually handle collisions if, in the very, very rare circumstance of 2 sensors reporting at the exact same time, this is what happens. So yeah, we have multiple sensors now, and that's very exciting. What can we do with this stream of data? Well, I wanted to get all the data first just into my database. I wanted it into a data structure where I can later on consume it. Now, some just really quick nomenclature. Let me go back. Anything that puts data into your stream, anything that feeds your stream is called a producer. And anything that takes information from your stream, doesn't take it out, just consumes it, is called a consumer. So once I have all my data going into a stream, I'm good. I'm golden. I have plenty of time afterwards to consume that data and make it do interesting things. So within this project, I have it feeding into a time series, which is basically a data structure that has timestamps, and with every single timestamp, there is a value associated with it. So Redis has a time series that I like to use, and I use that with Grafana, which is a visualization software as a service, and it just works really, really well. I can also store each individual location as a JSON document. So as I'm, idle, I can actually pull data from the stream and convert that little stream entry ID into a JSON object and store it within Redis natively, which is really nice because then I can actually call queries upon that, and I can query, temperatures between certain timestamp ranges of certain dates. I can look for locations by name, and I can look for locations based off of their average AQI. So, if the kitchen just tends to be a little bit higher AQI, which is kind of makes sense, when we're cooking, I would be able to find the top, AQI offenders in the kitchen would be up there. Also, the whole crux of having IoT is for having automation. So with this project, we actually have an SMS notification system. And so I'll go through that. All right, so let's actually create some time series. It's pretty straightforward. Once it's in the stream, now I need to read from the stream. So this is normal Python. This is not MicroPython anymore. So right here, we are reading from the stream. I'm reading one entry at a time, and you'll see a stream key, stream entry ID. So there's a lot of data. 5 seconds, every 5 seconds, I'm reading a sensor of, maybe 4 or 5 sensors active over span of a month. So there's a lot of data. So that stream entry ID is kind of like my placeholder, like, oh, I've already added this to the time series, so I'm just moving forward. So my result now contains basically that stream entry that has one target, one AQI reading, one PM25 reading, one temp reading. In my try clause, I'm creating 3 different time series. A time series for the temperature, time series for my particulate matter, and a little typo there, a time series for my AQI. So I can actually track those 3 individual values within their individual time series. So the temperature has no bearing on the AQI. So I can actually look at the temperature or the AQI over time with my time series. So this isn't too integral to the actual sensor setup, But I really like, again, I'm a visual learner, so I love Grafana. So I use it a lot just to kind of check on values, and it's very interesting. So this is a fast API endpoint where I am basically pulling information out of the time series and then feeding it to Grafana. And the interesting thing about Grafana is that you can look at more than one time series object. So if I want to look at the AQI and the temp at the same time, we need to be able to code for that. Also, you can look at multiple AQI readings within the house. So I can look at 4 or 5 different sensors at the same time. So I need to code for that. But basically, the big code that I really want to show you is on the right. Results equals redis.ts.range. So I am actually saying, hi, Redis, I want to look at your time series data structures, and I want to get a certain range of an existing time series data structure. And so that from time and to time, that's given to me as a request from Grafana. And I'll show you a demonstration of Grafana. And I want to tell it how I want that data compiled. So I want it averaged with a certain interval. So instead of having all the data points every 5 seconds, maybe I want to get an average of 30 seconds or a minute. That's a lot easier on Grafana. They're not going to have to chomp down on all those data points to make a graph. And it just makes sense. It just saves us on network. Cool. So this is what it looks like. Basically, this is in the spare bedroom. This is a few days ago. Air quality was okay. I think I was actually 3D printing in the spare bedroom when this was happening. So there was a little bit of funky air from the printing, the heating up of the filament. But yeah, it's not bad at all. And I want to show you now how we update and create JSON from the stream as well. And this is a completely separate script that I'm running of different from the actual time series. So again, we're going to read from the stream. We're having JSON stream entry ID. You see there, that again is a placeholder. So if the script breaks or my computer decides to log out or anything like that, it will know where it last picked up. So I don't have to start from the beginning 3 weeks ago of consuming this data. So basically, again, it's very similar to the time series that pulls out the particulate matter, the temperature, and the AQI. And it stores it in these JSON documents. And this is also a great opportunity for you to create a maximum AQI that it has seen, or a minimum. You can store, if we're doing this as a larger scale with a warehouse or a multi-property, entity, you could actually include, not within this script, but within this JSON, you can include geospatial coordinates for geo-indexing. You can have contact information, string values for specific locations on how to find the sensor. It's up in the rafter over up near those boxes. So I think it's really important to have JSON documents associated with every single sensor, just so you can have more enriching information about it rather than just the data. So I have this data that I'm reading from the stream, and then each stream ID, I actually, set a JSON document. Now with Redis, when you set, it either adds a new one or it just updates, which is really nice. So here, I don't know if I'm adding a new one or not, so I'm just setting it. So it'll overwrite any of the existing values that I actually have here. So again, here I'm having timestamp, which is pulled from the stream entry ID, and then particulate matter, temperature, AQI. And you'll see that last 12. I'll show you real quick what last 12 is. This is part of the SMS notification system that I wanted to put in here. So if I read my AQI values and all of a sudden it skyrockets to 245, that's not good air quality. If it happens just once, that's a fluke. That could be anything. That could be a neutrino flying from the sun and hitting the sensor in such a weird way that it would trigger a false reading. It happens a lot. So instead of just trusting one reading, I want to trust 12 separate readings. Why 12? Well, in my particular case, I take a reading every 5 seconds. So 12 times 5 is 60. So if I have an air quality that is of a certain value after a minute, if it's all consistently high, then it might be cause for concern. And I will, actually get a notification. I deem that is worthy of notification. So here I am pulling up my existing JSON. If I do not have an existing JSON, then I'm going to prep it by creating my empty array of just 0 readings. Otherwise, I'm going to just pull out my JSON's last 12 array. And I'm going to, this is within a previous file, by the way. This would be in my JSON consume script. I'm going to take the most recent AQI reading and I'm going to append it to my array. And then I'm going to pop the oldest reading. So it's always going to be like a sliding window of the freshest 12 readings. I'm going to take the sum of that. And if the sum of that is over specified AQI threshold, then that means that I actually have probably some pretty bad air. So that means that I should actually notify whoever I have for my SMS notification. For me, it's me, that the air quality is bad. So I don't spam people every 5 seconds with this user notified action. I'm actually having a flag where I will pause the notifications for an hour. So you'll see all the way at the bottom of this code, if some last 12 is over the threshold, meaning if we have bad air, I'm setting the variable has been notified to r.get user notified. User notified is a Redis string that will be present if if the user has been notified. If not has been notified, so if this user hasn't been notified, then we're going to alert them, tell them the location and the actual AQI average that has been noticed. And it's also going to set user notified. Now this is setting the string to 1 or numeric to 1, and it's going to have a TTL, which is a time to live of 3600. Now that's going to set this string to exist for an hour. So basically, while this exists, this phone number will not be texted. And this was very readily apparent as soon as we cooked in the kitchen and I had bad air in the kitchen and I was getting text messages like every 5 seconds. I'm like, oh boy, okay, I'm gonna totally go over my Twilio free trial here. So yeah, this is a basic notification system. And here's just a quick little script to run, a Twilio message. It's very, very simple. I highly, recommend it. And yeah, you basically send my little method here, alert, as a value and location, and it basically says, hi, the current AQI is 245 at kitchen. You don't need a whole lot of information. I could set up further things like you can respond to acknowledge, so it doesn't spam you again, or if you can have it just like, continue or escalate, you can have it send these text messages to other people or other entities. So yeah, that's like, my little hello world for this air sensor. And actually, let me show you what's going on here. This is the air sensor, and it is printed in a little enclosure because, it is circuitry and it is a little fragile. But basically, this port here, these are air intakes. So this is a fan that pulls air. It blows air out here and it pulls air in here. And between those 2 points, there's a little laser where it actually senses particulate matter. So it's really cool. And it's pretty basic materials, nothing too out of the ordinary. And I'll show you really quick what it looks like when it's connected out of the box. And here's this just little blue sensor. And then here is the Raspberry Pi Pico. So you really see how tiny it is. So this right here is all it takes. And you can couple those with the battery pack I have here You can't really see it very well, but this is a AAA battery pack that puts out 4.5 volts. That's the minimum required for the sensor and the Raspberry Pi Pico to send data wirelessly. So what else can you do with this? A ton. This is really exciting. This is where my brain just sort of caught on fire and I had so many ideas. You can send it to a web server and you can trigger electric relays. So the image I have on the right here, that's a relay. And that takes low voltage, like a signal from a computer, and it basically opens the gate for high voltage. So you can turn on things. So you can activate something as simple as a box fan. You can start an air purifier. You could have servos attached to your window to open or close your window. Or you can actually trigger your HVAC system to, vent a specific room. As you saw, I did text messages, so you can also send out email notifications, pager duty calls, things like that. With IoT, the possibilities are absolutely endless. You can also crowdsource your own hyperlocal map. So again, purpleair.com, they sell very well-made production quality air sensors you can install outside, and that goes to their main server, and you have a hyperlocal map. I love Purple Air because, regional or news station maps, they're slow. They try really hard, but they're very slow. And sometimes if you see a big bank of dirty smoke coming towards you, you look on the map and it's like, oh, it's great air. Go jogging outside. It's like, no, you need to have faster and more local data reporting. So yeah, you can actually have it connected to Alexa. I know Alexa loves IoT, so you can actually alert to the specific room. Hey, air's bad in here. What I would really love to do, and I'm going to do in the future, is create an actual active heat map of AQI air. So I noticed I have a kitchen and I have a solarium connected to the kitchen. And I noticed when somebody cooks in the kitchen, air actually vents into the solarium. And I never thought that would happen because I can see the air quality go down in the kitchen and then go up in the solarium after the cooking is done. Really, really interesting stuff that I would never have known. So that is my little presentation on, detecting and monitoring and acting on air quality with Raspberry Pi, Redis, and a little sensor. So check out this GitHub repository, take a screenshot of the QR code or anything like that. It has all the code necessary. So it has the Raspberry Pi Pico W code, the code for that simple little API for Grafana. Instructions on assembling your actual own unit. So I'm going to have 3D files. And I'll include a lot of the sources of statistics that I have pulled from this talk and sort of show you what I was looking at as I was creating this. And again, I am a developer advocate for Redis. So I actually lead online courses. It's self-paced, but I'm on the video all over the place. So you can go to university.redis.com. Also, I do a lot of YouTube videos where I explain a lot of data structures and methodologies of integrating Redis within your applications. It's not just the cache. Of course, we can cache, but it's more than just the cache. So yeah, thank you very much for attending my talk. This is actually my first talk at a conference. I'm super excited. And Python Web Conference has been so great and make me feel really comfortable. So thank you, everybody. And yeah, if you have any questions, go ahead and email me at justin@redis.com. And I'm always more than happy to talk IoT, talk, climate change, talk about smoky air, and talk Redis. So thank you very much, everybody. I really appreciate it.